So we've been talking about the motion of charged particles when we put them in potentials, therefore what are their changes in potential energies. What about just calculating the potential due to a collection of charges? We know that the potential due to a single point charge is kq over r. That is not a vector. It's got units of joules per coulomb or a volt. And that is the potential due to a single point charge. That means that if we take that point charge q, that there is a potential at a point P, which is a distance r away, and that potential V at a distance r away, let's make that a capital R, is kq over r. So if I want to find the potential due to a collection of charges, we found in an earlier lecture the potential due to a sheet of charges, and we argued that from the point of view of the fact that the potential, the change in potential is actually equal to minus the integral of E dot ds. I don't know if you remember that, but we found that and just used the fields, the known fields, to find potential. And that is a way that we can find potentials. But another way we can find potentials is to simply say that, just like we've done in the past, is that the potential at a point P is the potential due to all the charges, all the point charges around it, or all the point charges in its vicinity, and we can add up those potentials. So, for example, if I want to know what is the potential at a point P due to two charges, let's take two charges, Q and Q, and ask what is the potential at P. Let's make this an equilateral triangle. Same problem we've done many times, but same kind of problem, but this time this is what's important, is that V is not a vector. It's not a vector quantity. So it's a very different you'll see. It's going to change a little bit. So let's say that this is that each of these things is a distance s from each other. We're at equilateral triangle, and we want to know what is the V at P. If we know what the field is at P, we could just take this and say, okay, if we know what the field is, we've calculated the field due to these charges before, we could do the integral and find the V at P, but that's not necessary, right? The other way to do it is just to say, hey, we know the potential of a point charge, and the potential due to a collection of point charges, V total, is going to equal to the sum of the potential due to all the point charges in your collection. So we can just sum them up. So this is just another way of doing it. Either one of these are equally good. These are equally good. You can say break up your charge distribution into points and add up the potentials due to all the points. Or we can say if we know the electric field of the charge distribution, we can integrate to find the potential. And V total, by the way, that's just delta V is a potential difference between 2 points, and V is the potential at a point. If we define V equals 0 at some point, then V total is going to be actually the same as delta V. Okay, so let's just look at this from a point charge point of view. So the potential at P is the sum of the potentials due to the point charges. So it's the potential of the top point charge, which is KQ over S, plus the potential of the bottom point charge, which is, KQ over S. But note now, these are not vectors. So when we do this sum, it's not a vector sum, it's a scalar sum, so it's super easy to do. What is it? It's 2KQ over S. So that's the potential at point P, right? So the notation that I wrote down, right, is just the potential at point P is the sum of the potentials due to each of the individual charge Q's at point P. That's what I mean by the sum sign at P. And so we just find the potential of the top charge, the potential of the bottom charge, and we add them together because they're scalars. Easy peasy. So you got a clicker question now. Let's say instead of in my triangle, I've got a Q and a minus Q, and I want to know what is the potential at P. Choose one of your answers. You can pause it right now. I'm going to let you pause it if you want to take the time to come up with an answer, and then start it again. 3, 2, 1. Okay, your answer is that the potential at point P is equal to 0 because VP is equal to KQ over S, that's the one on top, plus K minus Q over S, that's the one on the bottom, and it's a scalar sum, and that sum is equal to 0. So here's a question. What if I take a test charge Q? Let's take a little red test charge Q and put it at P. So let's go ahead and put a test charge Q at P and ask, the fact that the potential at P is equal to 0, does that mean that that test charge is not going to move? What happens when I let go of that test charge? So that's your second clicker question. Let you pause it, and then I will give you the answer in 3, 2, 1. The answer is that it moves down. Okay, how do we know that it moves down? Having a potential of 0 doesn't mean it doesn't move anywhere. Remember, in order for it to not move anywhere, it's got to have either no net force on it, that tells you it wouldn't move from rest, or it can't go down in potential energy. But if the charge moves in the downward direction, right, there is a net force on it in the downward direction, because the electric field at that point, this is a dipole, the electric field of a dipole looks like that. Whoops, that was a terrible electric field, but looks sort of like that. And so the electric field is in the down direction, so it's going to push it down. It also means that the potential must go down in the downward direction. Certainly it does. As the charge gets closer to the minus Q, it goes to a more negative potential. As the charge goes farther from the plus Q, it goes to a lower potential relative to the plus Q, right? As the charge moves away from the plus Q, it goes to a lower potential. As it moves towards the minus Q, it goes to a lower potential. So there is a lower potential, and what it's actually going to do is the plus charge will follow the field lines, and the lowest potential is when the plus Q reaches the minus Q. So the highest potential would be here, and then the potential equals 0 there, and the lowest potential is there. Charges will always move from higher potential to lower potential, and the lowest potential is not necessarily 0, right? In this case, we can have a lower potential than that, right? Here's a lowest potential. Lowest potential is minus KQ over S. The highest potential is KQ over S. Actually, what I just said didn't really make sense, but there is a higher potential. There's a positive potential above the plus Q. There's a 0 potential halfway between, and there's a negative potential when we get closer to the minus Q. Okay, moving right along. Last thing, just to help you with your homework. Now, instead of 2-point charges, let's go ahead and make a line of charge. Let's say that we have a line of charge density lambda, and I want to know what is the potential at point P. How would I find that? Well, again, as always, you would say, okay, if I know the field of the line of charge, then I can calculate it from delta V equals E dot ds. Absolutely, can calculate it from that, where this is the field of a line of charge. Or we can say that V at P equals the sum of all of the individual DQs, right? We're going to break the line into a DQ, and we're going to sum up all the DQs. Since it's an infinite sum, it's going to go to an integral of all the dVs for each DQ. What I mean by that is that we take a single little piece DQ, we say that piece is a distance s away, and we say that the potential dV, just the piece of the potential at point P, due to dq is k dq over s. And so, therefore, the total potential at P is the sum of all the potentials made up by all the dq's. K dq over s. Sum them up. Now, notice what varies as I move along that line. What varies, our integral variable is q, but what varies is s. So we will then have to find a relationship between S and dq, by using the fact that lambda is equal to the total charge q over the total length. We can actually find a relationship, and you can look back when we've done this before and find a relationship between S and dq, because dq is our integral variable, and S is also a variable, right? Variable. So we've got to find a relationship between S and dq in order to do this integral. I'm not going to do that out for you, but I'm just trying to show you the concept, right? If we have any distribution of charge, let's do a half circle of charge. This is easier because in this case, the distance that we're going to be interested in doesn't change. Let's pretend that's a circle, and we want to know what is the potential at P. We can say, okay, we've got a dq, and that dq, we'll just call that distance r away, where r is not going to be different for any dq. So this way we don't have a variable for our distance, r, And so dV, due to a single point charge, is K dq over R. So therefore, V is equal to the sum of all the dVs, which is the sum of K dq over R. But now because it's a half circle, K and R are constant, and so then that's just K over R dq. So the potential is K over R. When you sum up all the dq's, we got the total charge of that half circle. And notice that was super easy integral to do because it's not a vector sum. So there's no components that we have to take. No vectors we have to take components of. How do you know that carrots are good for your eyes? Because you've never seen a bunny wearing glasses.